Good morning, students. In today's class, we discuss and study various theorems of Boolean algebra, and also we will prove the theorems using different methods. Basic postulates. Now, what are basic postulates? In Boolean algebra, various fundamental laws or theorems, these are called postulates of Boolean algebra. Right? First postulate says, if x is not equal to 0, then x must be equal to 1, and if x is not equal to 1, then x must be equal to 0. That means the first postulate says something about the basic two values given to logical variables, that is 0 and 1. If a variable takes the value 0, then it cannot be 1, or if it takes the value 1, it cannot be 0. That is the meaning of the first theorem. And the second postulate or the fundamental law states that the OR relations, logical addition, there are four expressions regarding that. First one, 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is also 1, and 1 plus 1 is 1. So these four expressions are related to the OR relations. The third postulate is about AND relations, that is logical multiplication. These expressions are 0.0 is equal to 0, 0.1 is equal to 0, 1.0 is equal to 0, and 1.1 is equal to 1. And the fourth postulate is the complement rules, that is 0 complement is 1 and 1 complement is 0. The diagrams for these expressions are given here. After knowing about the postulates of Boolean algebra, now we shall discuss a very important law in Boolean algebra, that is called the principle of duality. It states that starting from a Boolean expression or from a given Boolean expression, we can derive another Boolean expression by changing the following things. Change each OR sign, that is plus sign, to an AND sign, that is dot. Change each AND sign into an OR sign. Then change each 0 to 1 and each 1 to 0. Then the resulting expression is called the dual of the original expression. So this principle is called the duality principle. Thus, for example, we can find out the duals of the given expressions. If the given expression is 0 plus 1 is equal to 1, then its dual is 1 dot 0 is equal to 0. Another example, if the given expression is 0 plus 0 is equal to 0, its dual is 1 dot 1 is equal to 1. Now we will study some basic theorems of Boolean algebra. The first theorem is properties of 0 and 1. We know that 0 and 1 are the basic logical constants in Boolean algebra. So with respect to the logical addition and logical multiplication of these two values, we have four expressions which are called the properties of 0 and 1. These are 0 plus x is equal to x, 1 plus x is equal to 1, 0 dot x is equal to 0, and 1 dot x is equal to x. Here x is a general variable which represents any logical value. It may be 0 or it may be 1. The other theorems are idempotence theorem, involution theorem, complementarity theorem, commutative theorem, associative theorem, distributive theorem, absorption theorem, and third distributive theorems. The proofs of these theorems we will see now. We prove all these theorems using two methods. One method is using the truth table method, which is the simplest one. To draw the truth table, of all the variables, and we write the values to these variables, various combinations of inputs, and accordingly we write the output. The required columns we compare and come to the conclusion that the theorem is true or proved. The second method is perfect induction method. This is a method in which we substitute all the values for all the variables and then proving that the left hand side of the expression is same as the right hand side of the expression. Also sometimes we prove using partial induction, partial substitution. Only some of the variables we substitute with their values 0 and 1, and some other variables we don't substitute. Anyway, we come to the conclusion that LHS is equal to RHS, and thus we prove the theorems. Now we prove the first property of 0, that is 0 plus x is equal to x. Now let us prove this first using the perfect induction method. Substitute x is equal to 0, as you can see here, and the LHS becomes 0 plus x is equal to 0 plus 0 is equal to 0 is equal to RHS. Substitute x is equal to 1, then LHS is 0 plus x, that is 0 plus 1 is equal to 1, which is nothing but RHS. So by looking at the statements, you find that LHS is equal to RHS, and therefore the theorem is proved. Now using the TT, you can see here the TT is drawn, the truth table, 0 as the first column, x, the general variable x, as the second column. So 0 is 0 only, x can take 0 or 1. Accordingly, the column 0 plus x, the required expression, is obtained. 0 plus 0 is 0, 0 plus 1 is 1. Now by observing the last columns, see 0 plus x, the required expression, and x, you come to the conclusion that the theorem is proved since the column values are equal. As we have seen the proof of the first property, the remaining properties and all the theorems will be proved in the similar way. That is, first we prove using the perfect induction method by substitution, and the second using truth table method. Here are some other theorems of Boolean algebra, like xy plus xy bar is equal to x. The proof is given here using algebraic method. Here we take the x variable common from the LHS. We get x dot 1 because y plus y bar is 1 is equal to x is equal to RHS. And the other one is the dual of the first one, that is x plus y dot x plus y bar is equal to x. Wherever dot is there we have a plus here, and wherever plus is there we put a dot. So as you can observe, the proof is given here using the algebraic method. After studying and proving various Boolean algebra theorems, now we shall discuss two much more important and widely used theorems. These are called De Morgan's theorems. A scientist by the name Augustus De Morgan has derived two very important laws with respect to complements. The theorem 1 says x plus y whole bar is equal to x bar dot y bar. Second theorem is x dot y whole bar is equal to x bar plus y bar. That is, when an expression is complemented, then individual variables are complemented, but the sign is changed from or to and, or from and to or respectively. The proof of these two theorems is given here using truth table, and the algebraic method, proof using the algebraic method is given in another class.